Well, great. Well, thanks to be here. I couldn't have asked for a better intro from Dick. I think he hit on a couple things that are sort of core to what I'd like to share to you today. So, as I think a lot of people know, there's currently a lot of interest and capital flowing into AI for the physical world, and particular the field of material science, and for really good reason. The pace of new materials innovation is one of the rate limiting steps in addressing some of the most challenging problems we face. Things like clean energy storage and transmission to universal access to clean water. AI started to bring extraordinary capability to the front end of this problem, starting to predict and explore design spaces really at a scale and a pace that was unimaginable until just recently. But here's the reality, and it's exactly one of the things that Dick just said is our bottleneck isn't discovery. Our bottleneck is implementation. That is ultimately where materials innovation stalls, but it's also where the opportunity lives. Just to frame a little bit why this is such a challenge and why the applying AI to materials is such a challenge, we can look at a couple numbers. First, to think about the size of the design space. There's something like 10 to the 60th possible molecular structures that could be calculated. That's obviously a gigantic number. I don't know the word for it, but that is really an intractable problem from a first principles calculation standpoint alone. At the opposite end of the spectrum, the problem is we lack really the internet scale training data that's enabled the success of all of the AI that we see now being applied through modern LLMs. Collectively, we've only characterized something like a million or so materials, each of which has been both slow and expensive to generate. And finally, what's really important, again, germane to the conversation you guys were just having, is that the diversity of the end applications into which these materials have to be integrated is really broad. There's something like 400 million different distinct SKUs into commercial deployment of novel materials. And so ultimately, really good work's being done to address these challenges. We're well on the path to much more rapidly predicting and synthesizing novel materials in the lab. But better predictions and faster synthesis itself is not enough. Our ultimate bottleneck is the ability to scale, to integrate, and to qualify these materials in the ultimate end systems that operate in the real world. And this leads us to really the hardest truth that we face. If we treat the material itself as the deliverable, we're falling into a trap. And one of my favorite stories around this relates back to COVID. So many of you may remember, obviously, we all remember that time, but there was an interest in taking these PCR types of tests that could identify COVID in water. They were well proven in the lab. They worked extremely well. And the idea was, can we deploy these into our municipal water systems to be able to track the spread of this virus? The answer was, we could try that, but once we did, they stopped working. And this wasn't because it was a signal to noise problem. It was because the fundamental chemistry was different. And this isn't unique. The brutal reality is that this is common against nearly all materials deployments going from the lab to the real world. And what happens is that discovery of materials is really only 10 to 20% of the ultimate effort. The remaining 90% is qualifying these materials in their systems in the real world. And so as anybody knows or has followed things like autonomous vehicles or robotics, you've seen this pattern. Those systems were proven and worked very well in pristine environments more than a decade ago. But they're now just starting to be deployed in the real world. That same pattern is going to exist here, but we don't intend to follow the path of the outcome. We intend to address it. So ultimately, what does it take to start to address this and bring innovation and acceleration of materials innovation via AI? To ultimately deliver this, what we need is a system that's fully integrated and treats atoms and bits as equal class citizens. Yes, we absolutely need Accelerated first principles computation. Tons of great work going on there. Yes, we absolutely need these LLM inspired data driven techniques, and there's tremendous innovation going on there. Yes, we absolutely need automated high throughput synthesis in the lab. There is tremendous innovation going on there. But ultimately, we need to be able to take those technologies, integrate them together into the ability to systematically scale, integrate, and qualify those materials in real world systems. And the key point here, this isn't a temporary gap. It's not something that more computation is going to solve. It's a structural feature of the real world. And any intelligent system that we design must take this into account. If this sounds like a massive undertaking, it absolutely is. Ultimately, right, this is an industry scale problem and it demands an industry scale solution. The way I like to think about this is what we face if we are going to bring AI accelerated materials innovation to the world, we have to recenter the industry, much like the recentering in biotech and pharmaceutical development that's occurred over the last 20 or so years. Specifically, we need not just new technology, but a new way of working. We need to be centered around open innovation, collaboration, and seamless handoff between small technology innovators and large incumbents who have expertise in building these systems, bringing them to the world, qualifying them, and maintaining them. If we can do this, we can start to really compress this cycle of innovation and delivery from decades into years and to start to solve some of these challenges we face. Things like energy transmission, storage, clean water access, et cetera, et cetera. This, it's going to happen. You know, the only question is who architects it and how quickly it's going to happen. Bringing this to fruition is really where I'm spending my time thinking and working right now. And if you're thinking in this space and you're working in this space, I'd love to connect and talk about it. Thank you very much, Evan, for having me.